In this video, we're going to illustrate the Gram-Schmidt process. So let us look at our example. Let V be the vector space of all polynomials of degree at most 2 with real coefficients. And let's let our inner product be the integral from 0 to 1 of the product of the two polynomials. And let's let our set S be the standard basis, 1x and x squared. A couple things to note. Since S is the standard basis, we already know our set is linearly independent, which is one of the conditions to do the Gram-Schmidt process. All right, so the algorithm tells us to let our first vector in our new set be just the first vector in our original set S, so V1 is going to be 1. And V2 is therefore W2 minus the inner product of W2 with V1 over the length of V1 squared times V1. And this will give us W2, which is X, minus the inner product of X with 1 over the length of 1 squared times the polynomial 1. And now this is where we can do some scrap work. So we'll go a couple lines down. Scrap work. So there's a couple computations we need to compute. First, what is the inner product of X with 1? So based on our inner product here, that should be the integral from 0 to 1 of t times 1 dt, which is just the integral from 0 to 1 of t dt, which is equal to t squared over 2 evaluated from 0 to 1, which gives us 1/2 minus 0, which gives us 1/2. Next thing is we need to find the length of V1 squared, which is the length of 1 squared, which should be the inner product of 1 with itself. So based on how our inner product is defined, that's the integral from 0 to 1 of 1 times 1 dt. So that's simply the integral from 0 to 1 of 1 dt, which is t, going from 0 to 1, which gives us 1 minus 0, which is 1. All right, so then now going back up to our notes for what V2 should be, we get that this is going to equal X minus 1/2 divided by 1 times 1. And that gives us X minus 1/2 times 1. So then our second vector in our orthogonal set is going to be X minus 1/2. There we go. And then now we're going to go ahead and find V3. So V3 should equal W3 minus the inner product of W3 with V1 over the length of V1. Let's actually write it this way, with V1 over the length of V1 squared times V1 minus the inner product of W3 with V2 over the length of V2 squared times V2. And again, we'll need to do some scrap work. So our scrap work is that we have So now we need to find the inner product with W3 with V1. So this is going to give us the inner product of x squared with 1, which is the integral from 0 to 1 of t squared times 1 dt, which is therefore just simply t cubed over 3, evaluated from 0 to 1. 1/3 minus 0 is 1/3. All right, next we need to find the length of V1 squared, which we've already done in the previous step, so that's 1. We want to find the inner product of W3 with V2. So this is going to be the inner product of x squared with x minus 1/2, which is the integral from 0 to 1, t squared times t minus 1/2 dt, which is the integral from 0 to 1 of t cubed minus 1/2 t squared dt. Therefore, we get t to the 4th over 4 minus 1/6 t cubed, going from 0 to 1. So we get 1/4 minus 1/6 minus 0, which is equal to 1 over 12 when you simplify. All right, and then last thing is we need to find the length of V2 squared. So that's the inner product of V2 with itself. So the inner product of x minus 1/2 and x minus 1/2, which is the integral from 0 to 1 of t minus 1/2 times t minus 1/2 dt. And then that just gives us the integral from 0 to 1 of t squared minus t plus 1/4 dt. And I'm going to just go ahead and not do all of the computation, because at this point it's a little bit of algebra, but you should just get t cubed over 3 minus t squared over 2 plus 1/4 t, going from 0 to 1. And that final answer is going to also give you 1/12 when you simplify everything. So now we have all of the coefficients we need to compute V3. So actually, let's go back up to where we had our formula for V3. And we'll see that V3 is therefore now going to be equal to x squared, which is what W3 was, x squared minus 1/3 over 1 times 1 minus 1 over 12 divided by 1 over 12 times V2, which is x minus 1/2. And then that simplifies to give us x squared minus 1/3 times 1 minus 1 times x minus 1/2. And that simplifies to give us x squared minus x plus 6. So there's our V3. So therefore we have that our new set S prime, which is the set of vectors 1, x minus 1/2, and x squared minus x plus 1/6 is an orthogonal set. So you should be able to verify on your own that in fact S prime is orthogonal.